From IBM Quantum Research, and today I have the pleasure of hosting Cater from the University of Washington in St. Louis, who will talk about effective non-Hermitian evolution of a superconducting qubit. Hi, Cater. How are you today?
I'm doing great. Good to see you, Zlatko.
It's good to see you. Where are you tuning in from today, Cater?
Well, welcome to my kitchen, not far from Washington University in St. Louis. It's where I've been spending a lot of my time over the last few years.
I can imagine. Well, it's a pleasure to have you. Before we pull up your slides, Cater, allow me to give a bit of background and introduction to you. Cater received his bachelor in physics from Reed College in 2002, and his Ph.D. from the University of California, Berkeley in 2008. And working also with Professor Dan Stamper-Kern. Cater, of course, as many of you might know, is a man of many talents, working as a beekeeper. He's got great guitar skills, winemaking, if I am right. Pretty much anything you think of, Cater's probably done and is really good at. After studying also Bose-Einstein condensation and multiply connected geometries, Cater also went on to become a world expert in quantum measurements and performed some of the very first studies of position measurement quantum back action. After a short postdoc with Stamper-Kern group, this is where he joined Irfan Siddiqui's group, and I think I first had the pleasure of meeting Cater. In 2014, Cater joined the faculty at Washington University. In 2015, he received the Alfred P. Sloan Fellowship in Physics, and he's also received the St. Louis Academy of Science Innovation Award in 2017 and many other accolades for his wonderful work, as well as an NSF career and so forth. So I think with that, Cater, it's our pleasure to have you here today, and the stage is yours.
Excellent. Well, thank you for the opportunity to be here. And I'm excited to tell you about the research we've been doing at my group in St. Louis. And I've got a slight echo. I don't know if there's a way to back that off, but I can try to work through it.
Yeah, it should be off now.
Okay. So let's get into a talk about this research. And of course, I love questions as we go, and Zlatko will be great at jumping in and asking them if you have questions. So I want to start by saying that dissipation and decoherence are quintessential aspects of quantum optics. That is, if you have an atom by itself, sitting alone, well, that's a closed quantum system undergoing unitary evolution given by the Schrodinger equation, but there's no optics, so it's not particularly interesting. So if we want quantum optics, we need to think about open systems where now we have a dissipative coupling to the environment. And that dissipative coupling does a couple of things. It imbues that excited state with a lifetime, and those transition energies, or those energy levels, with a line width gamma. Furthermore, it necessitates a master equation treatment for the state, now described in terms of a density operator rho. That is, if we say start this atom off in the excited state, sometime later, due to its dissipative coupling with the environment, it might be in the ground state, but that master equation treatment reflects really a lack of knowledge about the state in between. At some point, we don't know what state it's in, excited state or ground state. Hence, we describe it with a mixed state. Now, that could bother you that, hey, we don't know what the state is. Is it in one state or the other? And so to rescue the wave function picture, we've actually, as a field, introduced something called a quantum jump. You could think of this as a conceptual picture that rescues the wave function description. That is, the idea is the atom evolves always in one state or the other, and it makes a discrete jump from the excited state to the ground state at some specific time. Of course, these jumps happen at random times, and so the not knowing when the jumps occur gives rise to this mixed state interpretation. I should mention that my gracious host has performed some of this beautiful research looking into the process of this quantum jump, what's going on in there. And of course, I'm sure many of your listeners are familiar with that wonderful work. The point I want to make is one about the type of detection we make and how that changes our picture of the quantum jump. Specifically, the picture of a quantum jump implies a certain type of detection. That is, we consider an atom that decays from its excited state to its ground state, and we have a photodetector that could, for example, give a click when it detects that photon. And so the story of the quantum jump really is driven by the detector. That is, the atom's in the excited state, the detector is silent, silent again, the atom's still in the excited state, and so forth and so on until that detector gives a click. At which point we know the atom has emitted a photon and is now decayed to the ground state associated with a quantum jump of its state, and then it continues to stay in its ground state. The point I highlight here is that there's a relationship between the state of the atom and the signal that we detect, that those two are inextricably intertwined. One of the first questions I worked on at Washington University was the question of what if we measure the emission in a slightly different way? That is, light has both a wave and particle nature. If we detect photons, we're detecting the particle nature. What about the wave nature? And of course, the wave nature of light pertains to quantum interference, that is, interference of that light with some other wave. And that wave nature of detection is characterized by a homodyne detector. So what we imagine is a scheme where this atom, as it decays from its excited state to a ground state, it emits light in the form of some sort of wave. And we ask, does it interfere constructively or destructively with some reference phase state? In practice, we realize this with a Josephson parametric amplifier operating in phase-sensitive mode. So we set up such an experiment, and we looked at the detected signal, and what do we see? Well, we see a bunch of quantum noise. This is, of course, what we expected. We're measuring the zero-point quantum fluctuations of the electromagnetic vacuum. And because if we visualize the quantum vacuum as some sort of minimum uncertainty state in this phase space of the electromagnetic field, we're just sampling from one quadrature of this field, and we expect to see Gaussian distributed noise. Okay, but since there's a relationship between the state and the signal, now that our signal is very different than just a click of a photodetector, what would be the new correspondence between the state and the signal? Okay, well, there's a long story about quantum measurement and various details of quantum measurement operators and so forth. But to cut to the chase, the way we think of this is each one of these digitized measurement values corresponds to a specific measurement of some component, something about that atom that emitted the light. And so we can break this noisy signal into a set of measurement operators and use those measurement operators to construct a piecewise continuous trajectory for the state of the system, which we can express in terms of the Pauli expectation values, expectation value sigma x, expectation value sigma y, and expectation value sigma z. The underlying physics of this measurement is the fact that the signal is proportional to the real part of sigma minus. That is, the coupling between the atom and the field is something like sigma minus a dagger. And we're measuring a quadrature of the field that's like a plus a dagger. And so we end up having a signal that's proportional to the real part of sigma minus, which is equal to sigma x. And so our measurement tells us about the x component of the spin. And then that has on top of it the quantum noise associated with electromagnetic vacuum. So the trajectories, this sort of quantum jump we infer from this sort of measurement of the spontaneous emission in the wave nature using a homodyne detector is as follows. We can imagine this thing starting off in the excited state up here. And then as the measurement result is at first negative, that corresponds to a trajectory pushing toward negative x quadrature, negative x axis on the Bloch sphere. But then the signal is positive. And so the trajectory is going to go over here to positive x. And the state kind of moves its way down to the ground state, the bottom of the Bloch sphere, kind of in a diffusive way on the surface of the Bloch sphere. That's what we expect. But of course, in reality, our measurements are not of unit efficiency. And so we have to average over different pieces of undetected signal. And so we end up with a similar evolution, something that's diffusively moving down through the state of the Bloch sphere, but is not a perfectly pure state. And of course, every time we measure one of these homodyne signals, we get a different noisy set of data, and therefore a different quantum trajectory of the state. So this is a very different picture of a quantum jump than what we saw when we think about photon detection. That is, when we think about photo detection, we think about these quantum jumps where we have a discrete instantaneous jump from the excited state to the ground state. Those jumps happen at random times, right? And of course, if you average over all those quantum jumps, we end up with a familiar exponential decay that's given by the ensemble average, the minus gamma t. When we measure the wave nature of the emitted light, we instead unravel the environment in a very different way. And we end up observing these quantum diffusion trajectories, where rather than jumping discretely, evolve sort of continuously, but diffusively down toward the ground state. Fortunately, if we average over all of those trajectories, we end up with the same exponential decay curve that we have for the quantum jump case. That is, these are different unravelings of the master equation. They both correspond to the same evolution when we neglect the details of the detector. Now, such a master equation is typically something known as a Lindblad master equation, which is the differential equation for the density operator rho that involves maybe some coherent sort of unitary evolution due to some Hamiltonian evolution, but then also two terms that have to do with the dissipative coupling to the environment. So one of those is known as the jump term, and the other is known as a coherent non-unitary term. So we've been talking about essentially a stochastic master equation, where we take this ensemble evolution and we add to it a stochastic update from the signal. And that update can be the information about quantum jumps from the detection of photons, or it can be information about the X component of the spin from the measurement of its emitted light in a homodynamic detector. And I told you this whole story just to get to a place where we're looking at this stochastic master, or this Lindblad master equation. And this allows me to point out another interesting feature of open quantum system dynamics, which is the following. If we somehow were to eliminate this quantum jump term from the dynamics, the evolution of the state would actually be described again by a Schrodinger equation, but a Schrodinger equation using a non-Hermitian Hamiltonian. That is, this new effective Hamiltonian is the generator of time translation, so long as we can pull this term out of the dynamics. Non-Hermitian Hamiltonian, that might sound quite odd, because we teach our students in graduate and undergraduate quantum mechanics that, in fact, a Hamiltonian has to be a Hermitian. And the reason we might make this convenient assumption is because if you have a Hermitian operator, it's guaranteed to have real eigenvalues. And in quantum evolution, that guarantees a unitary time evolution, that probability is conserved. That's awfully convenient. Additionally, when you have a Hermitian operator, you're guaranteed to have orthogonal eigenvectors, which form a convenient orthonormal basis to describe the state of that system. But if you really care about unitary time evolution, well, it turns out that you can have a non-Hermitian Hamiltonian. And this is a point that was first brought to the physics community by my colleague Carl Bender, who's also a professor at Washington University. So back in 1998, Carl and his colleague Stefan Becher published a paper indicating that one can in fact have real eigenvalues from a non-Hermitian Hamiltonian, so long as that Hamiltonian obeys a certain type of parity time or space-time inversion symmetry. So Carl is a mathematical physicist, and so he was studying a sort of a strange Hamiltonian corresponding to this harmonic potential with a weird imaginary term. Again, he doesn't have to study things that are particularly connected to reality, and so it's just an interesting problem. And what they discovered is that such a Hamiltonian can in fact have real eigenvalues. Now, Carl wasn't the first to point this out. In fact, this was observed or noted by a mathematician back in 1980, Emanuela Calcetti. But Carl's work really brought this to the physics community and ushered in a whole era of the study of parity time symmetric quantum mechanics, the idea that this was the real symmetry of quantum mechanics. And a lot of very interesting mathematical physics work took place in the early 2000s. But it wasn't until the mid-2000s that this discovery took on an experimental meaning. And that was with the observation that one can realize effective parity time symmetry in optical systems that exhibit gain and loss. And the most classic example of this is due to Dimitris Christodoulidis, who's at the University of Central Florida. So consider two optical modes. One of these has gain, so you can have optical gain, that's mode A, and one has loss, that's mode B. And the point is that these two optical modes have this parity time symmetry. That is, if we apply the parity operator, we flip these two modes. So mode A becomes mode B and vice versa. And then if we apply time reversal, well, gain turns to loss and loss turns to gain. And so now we're back in the same situation where mode B has loss and mode A has gain. Now it's possible to make experimental systems where we have modes with different levels of loss or gain. And so this ushered in an era of intense experimental work studying non-Hermitian systems with gain and loss. So one example of that is actually an experiment performed by Carl Bendner himself. So two coupled pendula, one that has damping and one that has anti-damping, but also experiments with electrical circuits, one with resistance and one with negative resistance, damping and anti-damping. We have examples in optical modes, gain and loss, and also with atoms trapped in an optical dipole trap where one of those states has loss.
Quick
I want to
question.
tell you about an experiment where, yeah, go ahead.
Maybe just to clarify for everyone in the audience, maybe if you could help define for us a little bit more that what the parity symmetry means, and parity of one system, what that means. If there's only like a harmonic or some kind of an oscillator.
So it's space inversion, for example. So if we think about two components, one on the right, one on the left, we exchange them. If we describe a system with say a 2x2 Hamiltonian, that's flipping the system across its diagonal or across its anti-diagonal. So x goes to minus x, for example. And in the case of these optical modes, it's really just switching mode A for mode B.
Great. Thank you.
So as I pointed out, the dynamics of a quantum system without quantum jumps can be described by a non-Hermitian Hamiltonian. And so in some sense, we expect similar physics to occur when we consider a quantum system with quantum levels that have imbalanced gain and loss. And there's a difference between these two systems, which I'll get into, which is that in the sort of mechanical, optical, or atomic modes, we consider modes with certain bits of population. But there's a hope that quantum systems, quantum non-Hermitian systems, will exhibit sort of quantum states, and we can consider the quantum phases that those states accumulate. Okay, to make this more precise, let's consider a common differential equation that we might encounter in mathematics. That's a differential equation where the time derivative of some n vector A is equal to minus I times n by n matrix B times that vector itself. Now, if this matrix B is Hermitian and constant, then we can look at the eigenvectors of that matrix. It'll have n eigenvectors, and it'll have n eigenvalues, and the resulting dynamics for this n vector A are the so-called trivial dynamics. That is, we take the overlap of the initial state with these eigenstates, and each eigenstate accumulates phase according to the eigenvalues. Now that differential equation may be familiar to you because you've encountered it in classical mechanics. And that is, this is isomorphic to a classical mechanical system where we have a system of n oscillators, it's n coupled oscillators. This matrix, this vector A represents a state vector that encodes the positions and momenta of those oscillators. The system will have normal modes and normal mode frequencies, and again, the dynamics are the same trivial dynamics that we have in the mathematical case. Or another place you may have encountered such a differential equation is in quantum mechanics, where we can consider n quantum levels. These n quantum levels are described by some Hermitian matrix we call the Hamiltonian operator. And there'll be the state will be described by a state vector psi, and that Hamiltonian will have eigenstates and eigenvalues. And again, the dynamics are trivial in that we take the overlap of the initial state with those energy eigenkets. They each acquire phase according to the eigenvalues. Now, we know from mathematics and also with extensions to quantum and classical systems that if B is Hermitian but time dependent, we'll have phenomena such as the adiabatic theorem, Berry phases, and Landau-Zener transitions. And then one can ask, what happens if we allow for any complex matrix B? Such a matrix might be realized in classical mechanical systems from having gain or loss. And in the quantum mechanical situation, can be realized by considering the dynamics of such a system without a quantum jump. Okay. The point of this talk so far is to illustrate that somehow the dynamics of some quantum system without a quantum jump results in effective non-Hermitian evolution. And let's see what happens. The first question is, how does one create a quantum system with no quantum jumps? One way to think about that is if we have a decaying atom and we somehow surround this atom with 4 pi steradians of detectors, and we just make sure that not one of those detectors clicks. That sounds pretty challenging to do as an experimentalist because one missed photon would sort of spoil the whole effect. But this sort of challenge is the sort of thing that inspires experimentalists to come up with clever ideas to make the experiment easier to do. And so what we consider rather is to extend the Hilbert space of this quantum system to 3 levels, and to use this lowest energy level as the effective detector for those quantum jumps. And what we'll do is we'll just focus on a new qubit that consists of the excited manifold of states, and we'll condition on evolution that leaves this qubit intact, which of course is much easier to do. I'm an experimentalist, and so experimentally, what we do is we have fabricated a transmon circuit, so one of the simplest superconducting qubit designs there is. This is a circuit that consists of a Josephson junction in a squid geometry shunted by a capacitor. And we embed this transmon in a 3-dimensional cavity. And most interestingly, what we do is we shape the density of states outside the cavity using impedance engineering techniques such that the decay rate of the energy levels of the transmon circuit can be engineered. That is, we shape the density of states to enhance the density of states at a certain frequency so that when we tune the excited to ground state transition frequency to match that enhanced density of states, we see much more rapid decay of that state than the other states in the system. So all told, what we do is we tune the system such that the excited state decays relatively rapidly with a decay rate of 8 decays per microsecond. But the upper excited state, the F state, decays comparatively slower, just 2 decays per microsecond, 0.2 decays per microsecond. So the experiments kind of take place like this in a cartoon schematic. We're going to initialize our qubit, say, in the F state. We'll then allow this system to undergo some sort of evolution under this effective Hamiltonian. And as I've depicted here, that evolution involves some sort of coupling between these 2 states at rate j. After some time of evolution, we'll post-select in the qubit manifold. That is, we'll make a high-fidelity single-shot readout of the state of this 3-level system. We might find that it's in the excited state. We might find that it's in the F state. But if we find that it's decayed to the ground state, the qubit no longer exists. And so we throw these experimental results away. So the evolution is realized in a post-selected fashion where only a subset of our data does the experiment actually work. Now let me give you a little intuition into the dynamics associated with this no-jump non-Hermitian evolution. What we have are effectively non-Hermitian Rabi oscillations. Okay, so we've started the system in the F state. We drive coupling between the F and the E state. And what I've plotted for you is the probability that the system remains in the F state for some specific choice of parameters. And what you would normally see is a Rabi oscillations that correspond to sort of cosinusoidal variation of the probability in the F state. But because of the fact that we've selected out evolution where there's a quantum jump to the ground state, there's an effective measurement back action that favors the F state. That is, it's unlikely that the qubit's in the excited state because the excited state decays. And so we see dynamics that are distorted, the Rabi frequency is slowed, and the dynamics favor the F state. So we see this sort of strange altered Rabi oscillations due to the back action of the effective measurement post-selecting on the no-jump evolution. Now, the full description of our system is as follows. We have this effective qubit formed from the excited and the F states. And we're going to couple those states with some Hamiltonian, which we can express as J sigma x, which is realized by a drive that's detuned by an amount delta from the excited state. So all told, that's given by a 2x2 Hamiltonian, but this Hamiltonian is of course non-Hermitian due to the decay of this excited state. Now, given that 2x2 Hamiltonian, it's straightforward to calculate the eigenvalues and the eigenvectors of this Hamiltonian. And those are given as follows. The eigenvalues are, in general, complex. They're given by this nasty expression involving an I under the square root that can't be simplified any further. So we have to consider the eigenvalues not just as a real number, but in fact as something that we plot on the complex plane. Furthermore, the eigenvectors can be expressed in terms of the eigenvalues and are in general non-orthogonal. So let's look at the eigenvalues of this Hamiltonian as a function of these two parameters, J and delta. And those eigenvalues take on the shape of Riemann manifolds. So here I show on the left the imaginary part of the eigenvalues as a function of these two parameters, J and delta, and the real part on the right. So you can see that there's very rich topology associated with these eigenvalues as we tune these parameters. And let me just draw your attention to one degeneracy in this system that occurs for a specific value of J at delta equals to 0. This is known as an exceptional point degeneracy. And to tell you what that means, let's contrast this degeneracy with the degeneracy of a normal Hermitian Hamiltonian, which we refer to as a diabolic point degeneracy. Now, a normal Hermitian operator will have degeneracies, but because it's Hermitian, the eigenvectors are guaranteed to be orthogonal. That's not the case for a non-Hermitian Hamiltonian, where we can have a situation where the eigenvalues are degenerate and the eigenvectors are also degenerate. And that can be seen when we look at the expression of our eigenvectors of the system. They're just given by in proportional to the eigenvalue and J. So if the eigenvectors are degenerate, so too are the eigenvalues are degenerate, so too are the eigenvectors. Another way to say that is at the exceptional point, the Hamiltonian is no longer diagonalizable. Now, there are a number of interesting features associated with these exceptional point degeneracies that occur for non-Hermitian Hamiltonians. And I want to jump right into the most interesting features that we've been exploring in our lab over the last year and a half. And these are topological features associated with that exceptional point degeneracy. So we have at least two tuning parameters for this effective Hamiltonian. And again, those are J and delta. And I want to imagine tuning those parameters in real time and seeing how the quantum states evolve. In fact, what I want to do is imagine initializing the system in the eigenstate of the Hamiltonian for an initial value of J and delta equals to 0. And then slowly tune those parameters such that the system adiabatically follows the instantaneous eigenstates of the Hamiltonian. And we want to consider a loop that encircles that exceptional point degeneracy. Now, if this was a Hermitian system, well, we know what to expect. We'd expect in this case to acquire a Berry phase of pi from adiabatically encircling a normal diabolic point degeneracy. That is quite surprising. One starts in an eigenstate psi, and we go around the degeneracy, and we come back acquiring a Berry phase of pi. So psi goes to minus psi, meaning we have to go around the degeneracy twice to get back to the same state. But the system is not Hermitian, and in fact, in this case, what one expects is much more complicated. We expect the Berry phase, we might observe, depends on the direction of the encircling, that it'll be therefore a chiral Berry phase. And furthermore, we expect that the states themselves do not map right back to themselves. That is, the prediction is if we start off in one eigenstate psi minus, and we encircle the exceptional point in a counterclockwise fashion, that state will turn into the state psi plus, which then if we encircle again, will turn into the state minus psi minus, meaning we have to go around the exceptional point 4 times to get back to the initial state. And the story is different if we go in a clockwise direction. That is, psi minus goes to minus psi plus. So there's our Berry phase of pi, but that state minus psi plus then maps to the state minus psi minus and so forth. So the mapping of the states and the associated Berry phases that are accumulated are very different from the normal Hermitian degeneracy case. Let me first show you this simplest effect, which is that of a state transfer or a mode switch behavior. That is, if we start in one eigenstate and adiabatically tune the parameters, we'll end up in the other eigenstate of the Hamiltonian.
And quick question, Cater, before we get into that. What happens if you run through the point instead of circling it, you sort of run right across it and then back potentially?
Right. So the notion of adiabaticity would be that we move slowly compared to the energy gap in the Hamiltonian. And so if we make a loop that goes very close to this exceptional point, then the energy gap becomes very small. We have to go very, very slowly. And so we may not be able to make that evolution adiabatically. So in doing adiabatic evolutions, we want to avoid these exceptional points, which are the degeneracies of the Hamiltonian, which are generally challenging for any kind of adiabatic evolution.
Gotcha. Okay. So I guess what happens in that case is that you're non-adiabatic, and then it could be much more complicated and depend on the path and so on.
Absolutely. And I'll show you examples of that here in one moment.
Okay. Thank you.
So to give you some intuition, what should happen as we encircle this exception point degeneracy, let's return to the Riemann manifold that describes the energy eigenvalues of the system as a function of those parameters. So here's the real part of the energy as a function of J and delta. And so we imagine starting in an eigenstate, that's one of these energy eigenstates that sits on this upper sheet. Now, as we slowly tune the parameter, we expect the system to follow the instantaneous eigenvalues until it reaches this branch cut in the real energy axis at delta equals 0, in which case it would flow onto the lower manifold and end up on this lower sheet. So we'd expect to see the system maps from one energy eigenstate to the other, even though the initial and final Hamiltonian parameters are the same. This might seem somewhat like a Landau-Zener transition, but in a Landau-Zener transition, you go from one eigenstate to the other with different initial and final parameters. But now, because we have the sort of imaginary, this axis of the energy, we have this branch cut that allows us to connect between these two sheets in this way. So that's a behavior that comes from the adiabatic evolution on the topology of the Riemann sheet. Let's see if we can observe this experimentally.
And I guess quite important here is that these two vectors aren't orthogonal, and that's maybe part to why they can correspond to the same parameters.
In fact, in this case here, these two eigenvectors are actually they're highly orthogonal in this case. We can start in a place where where the Hamiltonian is nearly Hermitian, that the dominant term is this J sigma x term. So one can consider these eigenstates as being particularly orthogonal, but you're right. As we follow the instantaneous eigenstates here, the eigenstates themselves become highly non-orthogonal. And that likely plays a key part in the switching between these eigenstates.
Thank you.
Okay, so the question is how to observe this experimentally. Well, what we'll do is we'll pair this initial eigenstate, and then we'll slowly tune these parameters over a time scale of 1.5 microseconds, pausing along the way and doing state tomography to determine what the expectation values of the different Pauli operators are. And so what we observe is as follows. We started off in one eigenstate that corresponds to where psi minus corresponds to the expectation value of sigma x roughly equal to -1. And we've mapped the system to the other eigenstate where the expectation value of sigma x is roughly +1. The dashed lines here indicate the instantaneous eigenstates of the Hamiltonian. So to the extent that the blue solid curve matches the dashed curve, we've done a good job following the instantaneous eigenstates of the Hamiltonian. But we haven't done a perfect job. You can see there are some wiggles here. These wiggles are exactly this breakdown in normal adiabaticity that you suggested. If the change in the Hamiltonian is too fast compared to the eigenvalue difference, we'll end up with non-adiabatic coupling between the two states, therefore resulting in sort of oscillations at the energy difference of the eigenstates. And that's exactly what we observe here. But overall, we see a fairly robust mapping from one quantum state to the other. If you like, we start with some initial mixed state where the expectation of sigma x is -1. We map to a final mixed state where the expectation of sigma x is roughly +1. But there's still some population in the other eigenstate.
And maybe you'll anticipate this in your next slide, but could you go slower?
Could we go slower? Yes, we can slow down. So of course, if we go faster, this issue becomes more significant. We end up with bigger oscillations because we have a larger non-adiabatic coupling between the two states. Now, if we go slower, we certainly can go slower. The challenge is that a whole experiment success rate is exponentially decreasing in time, because anytime the system decays, we throw the result out. And so already 1.5 microseconds is maybe 7 times the T1 time of that excited state. And so the success probability is in fact quite low already. And so if we go much, much slower, we don't accumulate enough data over the course of a graduate student lifetime to show you what we see.
Yeah, I was going to say you could just run it for 3 weeks in principle, right? But if things don't drift, but maybe the course of a graduate student lifetime is a bit too long.
So nevertheless, we can go slower, and it's actually a really fun case because there's this wonderful physics of counter diabatic evolution. That is, even though you truly go adiabatically may take too long, there's ways to add additional controls to the Hamiltonian to go much faster, but still maintain the system in the instantaneous eigenstate at each point in time. And that's this idea of counter diabatic control. And that's, of course, be something that applies. So you actually take the control and you go faster and slower in different places to sort of cancel out these unwanted couplings between the states and achieve adiabatic evolution for much shorter timescales.
Mm-hmm. Right. There is also one question that I missed, I think maybe from a few slides ago when you were talking about encircling the point. We can leave it to the end if it's a discussion that will sideline us. It's a slightly provocative question, but I'll float it up to you, and we can decide to take it now or later. From Alexei Galda: encircling the exceptional point is not necessary to observe non-reciprocal dynamics, at least in the model discussed here. It is a misconception that continues to propagate in the literature. What is important is in what direction you adiabatically cross the line of PT symmetry, but not the fact of encircling the exceptional point. There is no topology in this effect.
That's an excellent point, and I'll touch on that in a bit, and then I'll come back to it at the end. And so remind me to comment on that later.
Okay.
But
Yep.
indeed, the mode switch behavior is not the full enchilada. And as I talked about before, what about the phases? That is, the geometric phase accumulated by these quantum states that occurred due to this transport. I showed you this prediction that we expect to see this sort of mode switch behavior, which we can debate about what the origin of that is. But in addition, these states will accumulate phases, that is, analogies of the Berry phase from that evolution. Is it possible to see those Berry phases that we acquire due to the evolution? So what I want to know is, if I take an initial state psi, I apply an encircling to the exceptional point, I end up in some final state, either psi plus or psi minus. What is this geometric phase that we accumulate due to that evolution? So of course, to measure a geometric phase, we need to make an interference measurement. And so fortunately, our transmon qubit comes equipped with yet another energy level, which we'll label the H state, which we can use as a quantum phase reference to measure the geometric phase accumulated due to this adiabatic evolution around the exceptional point. So the experiments as follows. We apply a sequence of pi pulses to excite the system into the F state. We apply a pi/2 pulse to create a superposition of the F and H state. Then we take what's in the F state, we use that to initialize the eigenstate of the Hamiltonian. And then we spend 800 nanoseconds tuning the parameters J and delta to encircle the exceptional point. All the while, this decay from the excited state to the ground state is occurring. And then at the end of this parameter tuning, we can apply another pi/2 pulse to rotate either the psi minus eigenstate or the psi plus eigenstate into the state F, which would then interfere with the H state. By tuning the phase of this final pi/2 pulse of this effective Ramsey sequence, we can then observe Ramsey oscillations, Ramsey interference. And the phase of this oscillation is that geometric phase accumulated by our state. And of course, we can also determine the contrast of this interference as well. The point I want to make is we can have the opportunity to measure an accumulated phase for either the state psi plus or the state psi minus at the end of this tuning protocol. So there are, in fact, 4 different possibilities to consider. And we'll actually look at all 4 possibilities to get intuition about what's going on. So we can start in the state psi minus, we can encircle in a clockwise direction, and we can look at the phase accumulated on the state psi minus due to that encircling. We could also start in state psi minus, we can apply a clockwise encircling, and we can look at the phase accumulated on the state psi plus at the end of that encircling, and so forth and so on, 4 different possibilities. Now, we're able to measure the total phase accumulated by the quantum state as it undergoes this time varying parameter loop.
Maybe
in order to yeah, go ahead.
Pardon the interruption, Kater. Maybe a quick question from the audience here as we press forward in this, since you're using, the 4th and so forth, high level states of the transmon. Could you comment on the charge dispersion and how much of an issue that's going to be for this, and the charge offset that's stochastically moving the frequency of the H and F?
Yes. So this is the idea is that the states H and F have a lot of they have low T2, and their energy levels are actually split in certain ways. And so the observation, using those as phase references, is in fact quite challenging. The fact that this state is actually split by the different charge states doesn't cause too much of a problem. It just leads to certain times where it's harder to do interference experiments, and certain times where it's easier to do certain interference experiments. And so the time 800 nanoseconds is chosen as sort of a sweet spot of our ability to see high contrast interference between this state and the state that we evolve. And so despite all of these issues, we still do see high contrast interference at specific times. We can test the phases that we observe by varying parameters of the energy, for example, of these things. We find that that phase that we infer from this interference agrees very well with the accumulated integrated energy of those states over time. But our time at which we can do these interference is chosen to be the case where we see high contrast interference without too many of these issues causing us a headache. So with any phase interference experiment, it's important to get a sense of what you're measuring by varying a parameter and seeing how the phase changes. And the point is, here we're measuring a total phase, which is the sum of some geometric phase and a dynamical phase that simply arises due to the dynamical evolution of these quantum states. And so what we're going to do is we're actually going to change the size of this loop. So the loop can become larger or smaller, and this changes the overall energy scale of the quantum states during the dynamical evolution. So let me first show the total phases that we accumulate when we look at the state transfer from state psi minus to state psi minus. So we're looking at this geometric phase accumulated on psi minus for both clockwise and counterclockwise evolution. And what we see in this case is that the phases depend somewhat linearly on the size of the loop. That is the total energy of the states, or the average energy of the states over that loop. And so what we see here is a large contribution due to the dynamical phase, just the energy of those states that they accumulate. But if we look at the phases accumulated from when we look at the state mapping behavior, going from state psi minus to psi plus, here we might expect that the dynamical phase would cancel out. That is, the system spends equal time in the state psi minus and psi plus, so the dynamical phase will be canceled out. And indeed, in this case, we see that the phase is roughly constant over a large region of changes for the loop size. So this means that this dynamical phase is canceled. And rather what we see in this case is a robust pi phase difference between these two directions of the encircling. That is, we take one state, we tune the parameters to go clockwise around the exceptional point, and we see a phase of say 0, and we go counterclockwise on an exceptional point, we see a phase of pi. That's precisely this chiral geometric phase from adiabatic transport around the exceptional point that was predicted by Heiss back in 1999. Now, there are, of course, many issues that I've swept under the rug or haven't had time to explain in gratuitous detail in this talk. And the first, which Zlatko touched on before, is the notion of adiabatic. And indeed, it's challenging to go slowly enough to be truly in a quasi-static limit, just due to the time constraints of the experiment and the quality of the data that we're after. And in fact, for the relatively fast loop parameter times that we're applying, it's better to understand the evolution in terms of a Floquet Hamiltonian. That is, we're starting in an initial parameter space, we're making a closed loop evolution, so we can think about the effective Floquet Hamiltonian and the Floquet quasi-eigenstates of that effective Floquet Hamiltonian. And it turns out that in this case, we actually end up with a much richer structure of exceptional point proximity that tells us about what exceptional points we're effectively encircling. Another detail is the notion of the imaginary energy component of the qubit. And of course, imaginary energy corresponds to loss. And so when we see this loss, of course, then corresponds to, in some sense, a low success probability. Now, I showed you data where we tune the parameters and we see this nice mode mapping from the state psi minus to state psi plus for a counterclockwise encircling. But if we do the same thing with a clockwise encircling, we see very different results. In fact, here you can see there's a lot of noise in our signal. In one case, we follow a path where the loss happens to be low, where the negative imaginary part of the eigenvalue is small. In the other case, we follow a path of high loss, which is where the negative imaginary component is large and negative, and we end up with a significant amount of loss. And so in one case, we see a mode switch. In the other case, we don't really see a mode switch. And that's dictated by just the features of one path is lossy versus the other path. So this might be one aspect of the question you brought up about, is it necessary to circle the exception point? Simply seeing this mode switch behavior is not necessarily an indication, or is not necessarily due to the topology of the Riemann manifold, because it can just be explained by the effects of loss or gain. But I would argue that the observation of these phases is a somewhat more robust measure of something that's due to the topology of the exceptional point than just the populations one has in one eigenstate or the other. As a bit of an outlook, let me abstract away the details of our experiment and discuss sort of what this encircling behavior looks like in a more abstract sense. So we have a system with an exceptional point, and I'll call it EP2 because it's a second order degeneracy of the Hamiltonian. And there's some control parameter space. In our case, those happen to be J and delta, the amplitude and frequency of a microwave drive that creates that Hamiltonian. We considered a loop where we start and stop at the same place, and we apply this control loop so that we encircle this exceptional point, or maybe we do not encircle the exceptional point. In this case, where we encircle the exceptional point, what we've done is we've effectively exchanged the eigenvalues of the Hamiltonian. So initially, the eigenvalues on the real and imaginary complex plane are located here and here. And what this loop does is effectively swaps these eigenvalues with one to the other. One state goes to the other. Now, if you were to make a smaller loop, and of course we have done this, that does not circle the exceptional point, what we do is we expect that the eigenvalues change as we perturb the Hamiltonian, but one eigenstate will map to the other eigenstate. Or sorry, one eigenstate will map to the same eigenstate. So you see there's a difference between the two paths, whether or not we've encircled or not the exceptional point. And that's characterized by the winding number, which is an integer that describes how many exceptional points we've gone around. Now, the reason I rephrase it this way is because it becomes quite interesting to generalize this system to higher order exceptional points. That is, we could have a situation where we have now considered the E, F, and H states. Each one of these we control with a value J and delta. And so there's in fact four control parameters in the Hamiltonian, which would now be a 3x3 Hamiltonian. And one can tune those parameters to a place where there's a threefold degeneracy, which we note as EP3. So let's think about what the control around that threefold degeneracy EP3 might look like. So there's four control parameters. You can think of them as J and delta for each transition. And they're drawn here sort of schematically in this two-dimensional space. One can consider, one should note that there's connected to this region where there's a threefold degeneracy, there will be a surface in this control space of twofold degeneracies. That is, where just two of the eigenvalues are degenerate, but the other one is not. So now consider a three sphere that's a constant distance from the origin from this threefold degeneracy here. So some surface in parameter space that's far from the EP3 degeneracy. This surface intersects the surface of twofold degeneracies in a certain place. But because this three sphere is now a three-dimensional surface, I can make a projection of that onto three-dimensional space to visualize this control space here as a box. So we can control the surface of the sphere corresponds to the volume of this box, and the intersection of this three sphere with the twofold degeneracies occurs as a certain line inside this box. And most intriguingly, this line here forms a topology of a trefoil knot. in this box. And this is something that, in fact, Jack Harris's group has seen in their optomechanical system, and they reported on during the Murch meeting. Now, the idea of tuning parameters to encircle an EP2 degeneracy in this case becomes much richer. That is, consider 3 different controller loops, one that doesn't go anywhere near these exceptional point degeneracies, one that goes around this twofold degeneracy. Again, we don't want to go through the degeneracy because then we wouldn't have adiabatic transport. And then one loop that goes around 2 of these EP2 loops. Well, in terms of what the eigenvalues are doing, these corresponds to different levels of braiding of these eigenvalues. So the black path, where we don't go around anything, corresponds to just every eigenvalue gets mapped onto its own. The red path, which encircles one of these EP2 degeneracies, corresponds to the exchange of one eigenvalue with the other, while the third one remains untouched. And the green path corresponds to a swap braiding of all 3 eigenvalues. So in this case, one would say that the control loop is characterized by the non-abelian generators of the braid group over 3 dimensions. And so while we've been able to just encircle one EP2 degeneracy in our system here, extending this to a higher order degeneracies and characterizing this resulting Berry phases that one achieves from encircling these degeneracies will be indeed quite interesting. Okay, with that, it's the top of the hour. And before I pause for any further questions, I'd like to acknowledge the students and collaborators that have contributed to this work. The lead student on this project is Miriam Abbasi. She's a 4th-year graduate student who's led all of this work, assisted by postdoc Wei-Jen Chen and theory colleague Yogesh Yogalkar, who's at IUPUI, Indiana University, Purdue University in Indianapolis. And my former student Matsi Nagalu, who's now at MIT, really started this whole project and has been a contributor ever since. We've had really wonderful conversations with Jack Harris, who is one of the deepest thinkers in this area. So with that, I've got just some summary comments that I told you about 3 things, really, maybe. The first is the story of quantum trajectory, something near and dear to my heart, that by measuring spontaneous emission in a certain way, we unravel different kinds of quantum trajectories than one infers for quantum jumps based on photon detection. That gave me the chance to introduce this idea of a Lindblad master equation and ask what would it be like if we took away these jumps altogether, in which case we end up with this effective non-Hermitian Hamiltonian, which has complex energies and degeneracies known as exceptional points. Now, the final point is that we've dynamically tuned these Hamiltonian parameters such that the state encircles the degeneracy, and we see 2 things. One, we see that there's a mapping from one state to the other, but more excitingly, we see that depending on the direction we go, if we map from one state to the other, we observe a chiral geometric phase from encircling that exceptional point degeneracy. And extending this to higher order degeneracies will be a certainly interesting thing to consider in the future.
Thank you, Kader, for the wonderful talk. And I know I have a number of questions. Folks, feel free to post your questions in the comment chat box, and I'll try to get those to Kader as soon as I can. And there's always a bit of a delay between when you post them and when I get to them, so I apologize if I take a minute. I think Alexia was, by the sound of it, fairly satisfied by your answer to the earlier question on the PT. There was a follow-up to that, which is, what if your loop does not encircle the exceptional point, but crosses the axes 2 times? I think this was in the context of EP2.
Right. Let me see if I have a diagram here. So, yeah, so what happens if we so make a control loop that goes like this? Well, in that case, we would expect there to be no effect, so that looping around these 2 exceptional points would lead to, at least in terms of the state mapping physics, no change, that we'd end up in the same state. You can imagine taking this drawing here and connecting it to another one And we just would stay always on this blue Riemann manifold the whole time. So we wouldn't expect a state mapping effect there. Now, this is an interesting question about whether or not the geometric phases would, there would be no effect there or not. And I don't know offhand, but I imagine that those may cancel out as well. So encircling 2 exceptional points would be the same as encircling 0 exceptional points.
Okay, I think Alexi's not convinced. He doesn't think that's what simulations predict, but I think maybe that's going to be hard to follow.
Maybe you have to send me an email, because that sounds interesting, that we would maybe see different geometric phases. But based on the shapes of the Riemann manifold, we'd expect, and we'd see in our experiments, that going around 2 exceptional points is the same in terms of the populations as going around 0 exceptional points.
Wonderful. I'm glad this seminar can generate some discussion there. So maybe the two of you can, unless there's kind of a productive discussion here, the two of you can take that in a private email. Otherwise, our next question from Karthik is, what is the anharmonicity of... Alexi, by the way, says it's all good. Thanks, Kate. Karthik says, what is the... Thanks, Alexi. I think these are good questions to raise, and it's always good to have a more... non-unanimous, agreement, but to have people disagree, a little bit of scientists, and probe each other. So that's part of the process. Karthik's question is, what is the anharmonicity of the qubit? And maybe that's the first part. And why does the qubit go to the second excited state due to back action?
Right. So the anharmonicity of this transbond is 300 megahertz. It's a very standard transmon qubit. And that's important so that we can, so we have to create a fairly narrow band feature in the density of states of to which the cavity couples and to which the qubit decays, in order to selectively have decay of one state and not the other state. So that's that was achieved by various microwave engineering techniques by adding impedance engineering. Now, the second part of the question is, why does the qubit go to the F state? Why does the dynamics favor one state over the other? And you can think of this in the sense of a Bayesian measurement back action. That if the state E decays very rapidly, and so if you say, hey, it hasn't decayed, and you say, well, then definitely it probably isn't the state E, because the probability of it decaying and being in state E is very high, but the probability of decaying and being in state A is very low. And so the fact that it hasn't decayed by Bayesian inference means that it's in the state F with larger probability. And that's a really intuitive way to understand the effective non-Hermitian evolution as favoring one state over the other.
Great, thank you. I think maybe to relate to that, how much do you tune the J and the delta in the experiment, sort of with the realistic experimental parameters?
Yeah, I probably, I may have one slide that has actual numbers on it.
Just ballpark is fine.
Yeah, ballpark. So typically J is initially 30 radians per microsecond, so it's 5 megahertz or so. The exceptional point, the J that corresponds to the exceptional point, is something like 5 radians per microsecond, so 1 megahertz of coupling rate between the states. And then the detuning typically tunes plus or minus 30 megahertz as well. So these loops are rather round, but we start much further from a bit further from the exceptional point that's indicated in this drawing here.
I see. And if delta was 1 megahertz or something, you would just have to go a lot slower, right? If the
right. So if delta was really small, we'd have to go slower. And so we choose a large value of delta so we can spend, that there's a large energy difference for most of the time. The energy gap does become quite small when we get into the between the two exceptional points, and that's that's where most of this non-adiabatic coupling between the two states takes place. But the interesting observation from our work is that the notion of adiabatic is a little bit, it's hard to realize an experiment. And in fact, we're working in a case where we should understand it in terms of a floquet Hamiltonian, that if you now periodically vary the parameters, what is the new effective Hamiltonian? And in this case, what was originally sort of one let's see, it would have been one value of J that corresponds to the exceptional point, gets spread out in space and takes on this sort of highly periodic behavior depending on the sweep period. And so one can actually, operating this Floquet limit, choose a sort of parameter space that gives you an effective encircling of the exceptional point where the eigenvalues become highly degenerate without going impossibly slowly. And the fun finding that we have is that we see the same chiral geometric phases from that evolution than we do if we go really, 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 really slowly. And so if we want to someday use this complex energy landscape for some sort of useful control, we'll of course have to do it very rapidly for it to be meaningful. And so this Floquet understanding allows us to harness that topology, but on timescales that are much slower than it would take to be fully adiabatic.
That's awesome. So basically, two immediate avenues are just keep adding more levels and more degeneracies. The other one is, move in a Floquet basis where you end up with maybe the same matrices effectively, but now things are moving rapidly because you're modulating at a high rate. If I could crudely summarize that.
Yeah, that sounds about right.
Okay.
And one of the most interesting things we can do next is we can consider spin chain with some sort of this non-hermiticity. So more of a many-body system, and what are the things we expect to see here? And there's certainly ways to generate also non-hermiticities without this post-selection technique. That is, we need to have sort of asymmetric hopping from one site to the other is another way to have a non-Hermitian interaction. And so we're working on ways to create dissipation-free non-Hermitian systems that should still exhibit these exception point degeneracies in a lot of this physics, but without the painful cost of throwing away 90% of our data.
Excellent. Thanks, Kater. There's a question here on, is there a paper about this presentation? And I guess maybe your last slide helps with that, but or maybe there's another preprint coming out.
There's a preprint on all of this. So we've published one paper, two papers, on one paper in Nature Physics, one paper in the archive on this, but the paper about these chiral geometric phases and this Floquet encircling is forthcoming. So we should have a preprint on the archive perhaps in a month or so.
Wonderful. And kind of a follow-up from Carlos here to that question was, how are these complex eigenvalues related to the complex values of the Bateman Hamiltonian, which is for harmonic oscillators, as far as I remember, although maybe you can apply for qubits, where you basically have quadratic two oscillators, I think, with p squares and x squares, and then you have some linear coupling between them between x and p. So maybe that's a very specialized question, but perhaps the question is more about relationship to what happens with not qubits but oscillators and potentially composite systems instead of individual systems. But maybe there's an interesting effect with composite systems. What if you had 2 qubits or 3, and you looked at systems like that instead?
Right. So I'm not particularly familiar with the Bateman Hamiltonian, but I can say that in sort of classical oscillatory systems, there's all sorts of different ways to create non-Hermitian dynamics. And one of those is with having sort of non-reciprocal coupling between the two devices. And that may be the physics that's taking place there. In our case, I think there are a lot of universal features having to do with these exceptional point degeneracies. And this sort of chiral geometric phases is one of those universal features that we just think about the topology around that degeneracy, which is quite generic. that also makes me, gets to my point of it certainly will be interesting to consider now systems that consist of multiple quantum states with perhaps different types of coupling between the states, where we do see other ways to generate complex energies and exceptional point structures. And there's a lot of work in the classical domain teasing out different aspects of this that should hopefully be used as inspiration for experiments in the quantum domain. Challenge for us is to find phenomena that feel somewhat uniquely quantum mechanical. And this is also a challenge we find in discussing with referees about the value of our work. Our system is truly a quantum energy levels with no classical analog, but due to this point I made about the mathematical isomorphism between classical oscillators, the mathematics is very similar. And so that's both fruitful and makes for some results to not be as surprising as other results, because they can be seen in classical systems.
Good, thank you. Perhaps any final questions, folks? And if I missed your question, please post them in the chat, because I think that's most of the questions I had from the audience. But one other question that I was interested in that we glanced over in the beginning was if you could talk a little bit more about the shaping of the environment. Oh yes, and this is a good site. Definitely go visit that. I think you had an IME and shaping the density of states outside the environment. What was it that you actually did there, and how was it done? Like, what was the technology or technique used in that?
Yeah. So we explored a lot of different ways to engineer the environment outside the qubit, and what we ended up settling on is so IME stands for impedance mismatch element, and so this is just a highly inductive element of a part of the transmission line, which we made from just rapidly changing the impedance of the 50 ohm cable that connects these things at a certain distance. So there's maybe a half a meter of cable, and then there's this impedance mismatch, and that leads to this sort of sharp density of states exactly where we want it to be in the energy levels of the qubit. So quite simple technology to shape that density of states. And of course, it's interesting, and we're working on ways to sort of have tunable in real time types of impedances, so we can tune this dissipation, which would be yet one more control knob that would be interesting for our dynamics. So tuning this gamma in time can actually lead to a lot of interesting effects that can actually lead to sort of preserving coherence in this manifold, even in the presence of dissipative coupling to the environment.
And question there. So I guess this is, you said, an impedance mismatch filter. How broadband is it? And I think you had another paper on this that I'm recalling, but essentially, you're also setting up a set of standing modes, I guess, there between your cavity and this, which are pretty high Q, most likely. I'm assuming this is not a copper cable that's connecting them. Maybe it is. And I guess at some point, you might have some revivals, or you might have, your bath might not be. Yeah, so maybe if you explain that curve also, that would be nice. I guess this is the energy relaxation rate of the excited state as a function of the flux. So you're kind of scanning over your impedance.
Right. So if we zoom in on this feature here, and I put a frequency axis on this, the bandwidth of this sort of enhanced dissipation is of the order 10 megahertz, something like 10, 20 megahertz. And so it's certainly it's not a Markovian environment for our system, especially if we're talking about energy scales that are large compared to that. And this is actually a subtle adds to some subtle features there. So if we manage to operate our system right here on resonance, in fact, as one turns on changes J, the the density of states that become relevant actually changes slightly. And so you get to a place where the effective dissipation shifts a little bit. Now, there's all sorts of interesting physics to be played with the colored density of states, that if we arc it on the side here, we can have enhancement of one decay process over another, and there's certain asymmetries that arise. We've studied that in various contexts, but the critical set of numbers is that we need this bandwidth of 10 megahertz to be, 10 has to be much less than, say, 300 megahertz, which is our anharmonicity, so we can selectively add dissipation at one level, but it also should be much greater than, say, JEP, which is typically like, I don't know, less than 1 megahertz. So that the environment is effectively Markovian over the relevant energy scales for our non-Hermitian dynamics. And that's something we are able to achieve quite comfortably in this setup.
And maybe the naive question, but what happens if you had a very long-lived qubit here, let's say 200 microseconds, and would you remind us, would you still need all the dissipation engineering for that, or could you perhaps get away without it?
So, I mean, the critical piece is this hierarchy of decay rates that ideally we would set this decay rate simply to 0. And the relevant thing is just the hierarchy of decay rates. If we go to very small gamma E, then all of the energy scales become very small, and then the time scales become longer, more subject to other issues. So we found it to be advantageous to work with a very strong dissipation and do the experiments relatively rapidly. I'll note that any residual quantum jumps given by this decay rate here, in this manifold here, you would think, oh, it's just a little bit of dissipation on our system. It turns out that any dissipation in this upper manifold of states plays a very significant role beyond just damping coherences. And in fact, the sort of energy scale of this dissipation starts to play a more significant role here. And so you see all sorts of counterintuitive effects that you wouldn't see in just the regular dissipative qubit due to the non-hermiticity. We have a whole paper on that we put in the archive, maybe a couple of months ago, understanding the role of quantum jumps in this non-Hermitian qubit manifold. And describing that requires this hybrid Liouvillean Lindbladian description of the quantum state. It becomes quite mathematical, but it's a challenge to deal with, and something we certainly have to pay attention to in a lot of our work.
Okay, wonderful. I think seeing as we're about 20 minutes over, I think maybe even though there's more questions pent up, we will have to cut it short there. I think, Kater, maybe if you'd like to share with us any final words or comments or thoughts, this would be a good time.
Thank you all for joining me. We're not actively searching for postdocs, but I'm always looking for wonderful postdocs and students to join in this research. And I love brainstorming and thinking about interesting sort of fundamental off the beaten path questions in quantum mechanics, such as this. And so I invite you to shoot me an email if you have questions or ideas or want to start a collaboration along these lines. I think it's a tremendously interesting field, and there's lots of different ways to go about it. And there's a lot of interesting ideas out there. So feel free to get in touch with me.
Wonderful. Thank you, Kater, for the wonderful and awesome talk and the very friendly ending. And also thank you to the audience for tuning in, for all the wonderful questions. This talk will stay recorded, and you can go back and rewatch it. Otherwise, we will see you next Friday at noon Eastern Time on the Qiskit Live Quantum Seminar Series. I was your host, Zlatko Minev. Thank you, Kater, and thank you, the audience again, and we will see you soon. Take care.
Thank you, Zlatko.